20 minutes already. Okay, good. So please download the Docker image or start downloading. Or if you downloaded the Docker image before, run this command anyway because it has been updated. And by the end, I will even say what is the update. And greetings to everyone there. So it's very nice to have you in this tutorial. If you don't have Docker installed, here's the link to the website, which have very good instructions how you can install Docker and actually go. But it's already 2:10, so we will have to proceed. So once again, I'm saying this full Docker. So
someone needs to mute. I muted him.
Oh, all right. So this is a short plan for this tutorial. It's going to be a full simulation tutorial using this G4e EIC. So first, I will actually give a short introduction to what is the software is going to be used for this tutorial. Then there are going to be two parts of interactive tutorial. For the first part, we will actually learn how to run the simulations. Right, how the simulations interact with reconstruction and actually build some plots. And the second part, which is the major part, we will take this luminosity monitor, which was presented by Yaroslav in the morning, and we will add this to the G4e, so this part will be about this. So then, we'll switch back to the presentation, and I will actually answer the most common questions, which usually arises. And then there will be official adjourn. But actually, people who have the tricky questions or kind of want additional questions can stay, and I can show maybe some additional details, additional elements, maybe go to some code, whatever. So that is the plan for this tutorial. So let's go back to talk about the software which will be presented today. Here is the most simple. I know that here is the most simple actually diagram of the software with generators on the top and reconstruction analysis on the bottom. This arrow on the left actually says that sometimes you just want to process the generator output of the generator, but then you need a fast detector simulation. We had this tutorial on January 9th, and certainly finally you have a full detector simulation. So today this tutorial will cover actually this part, and this tutorial will be actually repeated on February 6th, probably. So what is the software from this Docker container? So for Monte Carlo, we will use some samples from PFA, Beagle, Heroic, actually, for this tutorial, especially Heroic. And for this full simulation, we will going to use this G4 EIC or G4e, which is actually a pure jump implementation of two beamlines and J-like detector as of this point. And shortly, there will be one example how we can use this our reconstruction framework Java with this. So we'll come to this. So what is this G4e? Actually, Marcus already presented this slide in the morning, so I will not go into details. But this was our kind of standalone Jant application, which we use in Jefferson Lab. But recently we started adding, for example, another beamline. So there's actually now two beamlines. And the idea of this software behind what is written over here, that it can open several related to EIC Monte Carlo files, right, was that you can actually compare different things with one package, simulation package. For this tutorial, we'll also use Jupyter Lab, which is now pretty popular. And yes, let's actually dive in, and then we'll go through everything while we're doing it. So please, if you, once again, haven't downloaded Docker, let me get to some link. First, run this Docker pool electron ion collider epic. And if you've already done this, please run this command in your browser. It's a little bit longer than previous, because previously now you have to write this electron ion collider. And we actually, if you have been, if you visited our past simulation tutorial, we actually using normal code. So please run this string in your console. Let me do this. So fortunately I have it in my history. So all right, no way. How this happens. Yeah, one more thing for this tutorial. So that's probably a good example. I don't know why this happens right now on this machine. So guts of the tutorial is not happy with me. So I have already port 888 and 609 blocked. So I just changed it. So for my system, it's going to be in other ports, but you just will have it on port 888, and the another port will be 8080. So then open the browser. And my suggestion actually to open the private window, because sometimes actually ad blockers have something to do. And please open the local host. In my case, it will be 9999. In your, it will be 8888. So that is something that you should see there. So and once again, it provides you the output provides you two links. So at this point, we need this 8888. So can somebody confirm that it's working, that it also got to this step? Yeah. Okay. Good. All right. So we start with this Jupyter Lab, and on the left side, let me actually switch to presentation mode and maybe do my screen a little bit larger. In previous tutorials, we went to the 0.1. Now we go to the folder 0.2 full simulation tutorial. And we open file 0.1 dive in IPython notebook. That is what you should see there. So as you can see, if you actually scroll the file contains some text and then some code and some plots. So this code and this plots actually, it's a part of the Julia OpenCharm analysis. So it's pre-made in C++, and now this notebook just renders the plots. So you also see that the plots are not interactive. So in this tutorial, we'll plot another plots and they will be interactive. But this actually is still good, and you probably already saw this if you've been on fast simulation tutorial in the beginning of January. But it's still a good kind of dive-in example to introduce to Jupyter Notebooks. So I know that many of you already worked and know Jupyter Notebooks. And I know that some of you were on these tutorials on January 9th, so you already played with that. But for those who see it for the first time, so whole this environment is called Jupyter Lab. So, and this document, which is 0.1 dive in, is called Jupyter Notebook. As you can see, the Jupyter Notebook consists of cells, and cells might be the text, and it might be the code, and the code might be in Python or in C++. So we will use the Python over here, but in general, C++ root macros are also possible, more or less, to do all the tutorials that we are doing right now. So if I double click on the OpenCharm on this text, it actually converts to the, this is called Markdown. It's pretty close to a wiki if you don't know what is Markdown, how it's done. So, and if I actually click on this play button, small play button on the web, it actually executes the cell, and this time it will convert the text back to its rendered. So this blue thing on the left, it actually marks which cell is active right now. So right now the print hello EIC is active, and this is the code cell. And if I hit the play button, it will execute, and yes, it returns the hello EIC. And as you can guess, looking at pictures, the text might be not on the output of the cell. So if we play the next cell, it will actually renders the lattice formula. And actually, Jupyter Notebook works pretty fine with LaTeX. So if you would like to have your articles, science articles, kind of more interactive, you can use Jupyter Notebooks, everybody. Right? So now let's actually go run some jaunt, right? So please proceed to the 2.1 or 2.1 process MC file example over here. So what you see here actually is a Python library called G4e Py, which allows you to easily configure and run this jaunt G4e in using the Python and using these Jupyter notebooks. So first thing is just import the stuff. The second does configuration, and for this configuration we choose the master detector, as we call it, master detector J-like, beamline URIC. We will read the HepMC file, and it's smart enough to identify that it's HepMC file. The output should be hello, then beamon should be 200, so it should generate 200 events. If I just put this G4e over here and run play button and say that it's configured and ready to run, and we run it. And it actually initializes jaunt and start processing the events. So now the jaunt is running, and while it's doing it, I can a little bit look over here. So if you actually don't want to run everything in Python, or you don't like the Python at all, we are absolutely not hiding what's happening inside, and the strong comment what happened. It runs this G4e command with a script named hello.run.mac and with output hello. And as you can see, by the way, it's processed already. There is this file that's generated from our Python library, hello run with Mac, which actually have a standard jaunt macro file with all those parameters set into it. Then just run it. So even if you don't want to use this Jupyter stuff and whatever, it could help you to learn how you run this stuff and kind of operate this thing, but then you can just use a console without all this stuff. So you see there's a bunch
Now, can you hear me?
Yes.
I have one question. Would you recommend to generate large samples in this way with Python and Jupyter, or would you recommend to use something else? Let's suppose I want to generate 1 million events. Is it feasible?
That's a very good question. I actually will answer this several times during this presentation. So please, I will kind of have slides about this, and we will go into details what's happening besides, right? So, and I remember this question. I will actually specially kind of emphasize what you are asking. Okay?
Okay, good.
So, okay, it generated several files, and one of them is hello.go.root. One of them is hello.go.gdml with a GDML with geometry. And this is hello.go.root. If you double click on it, it will open this root browser. It's from the root 7. So we are with root team actually working on it to, they officially kind of say that it's going to be a new tab browser when they finish it. So, but right now we are using those pieces in this thing. And we see that this hello.go.root has the detector.go, and if we click on it, it actually opens the load logic. If we click right button down on it and click draw, it actually should draw us our detector. So here's our G-like detector with right now with Rick beamlight. And on the bottom, if you see this small buttons hidden on the top, there's a square called toggle control. And you can actually clip this detector, for example, like this. And actually, this is one of the if 7 thing. And the question is, can you actually render tracks with it? Okay, let's skip this question for now. It's actually coming. So, but right now, let me go to the solenoid. Okay, and I will show you the planes of the solenoid because we'll. Oh, not solenoid, sorry. For vector detector, because right on the next example, we will draw some. Yeah, so here it is. Here, for example, the planes of the vector detector. And we will actually, right on the next file, process it and plot some occupancy plots for the detector. So right now, the question is, what is this viewer and should we interact with it or not? So we are actually working, once again, root team is working on it to have enabled this thing. So Jant team is actually working to provide those messengers and stuff like this in Jupyter, right? But right now we will cover not only, I will just go ahead and say that we will cover not only showing this interactive state in Jupyter, but we will switch to VNC and also look like a more usual Qt interactive display. But okay, let's go back to some other files. So one of them is actually hello root. Which actually has some events and it has some flattened tree with hits. And for example, if I actually click here on hit underscore z, I see the hits distribution by zip. And also there is a file called hello run JSON, where actually this Python library put all this configuration that was used and actually all the information it has before. And actually, this library can load this file. And for example, if you would like to say, okay, I want to run the G4e with the same configuration as you, the only thing that's needed is this JSON file out of the run. So let's go forward and actually process some outputs which we've got. So we will processing this root output file, and there are four different ways how you can actually process root files right inside this.
Sorry to interrupt.
Yes.
I'm looking in the O2 full sim tutorial on my machine, and I don't see as many entries in my list on the left.
So so that probably means that you haven't updated. That's exactly why I asked you to run this command docker pull electron ion collider image, because probably you have an older version of the tutorial.
Oh,
so
I ran it at 12:45.
Yeah, so probably you can just close the image, run this command, docker pull, and by the way, okay, probably yes, and yeah, just in case you have a PDF file of this presentation on the left, so you can open it right in Jupyter Lab and have all the slides over here. But it was downloaded with this update.
Okay, I'll try to refresh. Thank you.
Yes, you still have time actually, because right now we'll be clicking just forward, and real coding will be on the second part. And this actually for those who are just downloaded Docker. So if you are still downloading it and not participating, it's okay. You probably have a chance to download it while the second part of this presentation begins. But let me quickly go back. So right now we'll be opening this root file and actually process it. On January 9th, we showed how to do this with TT draws. There are different ways how you can do this right out of Jupyter. One of them is just using root scripts. Another is, for example, using this new root R data frame. But this time we'll be using kind of Python tools. We'll use uproot library, which allows you to open and iterate over root files without root installed. And we will use a data science tool to do it. So please, this time we will not click each cell. We will just put run on the menu and then press run all cells. And it will take some time actually running the cells, and I will say what's happening. So here is just, first cell is just include. And then I will not go into really details. I will just say what happens. And then we just say for this uproot library that we want to get hits XYZ, their energy loss, and get the volume names in which it occurred, right? Then we create so-called the pandas data frame. So if you don't know what is the pandas data frame, it's probably my recommendation actually for you to look into it, because it's actually written in C, not even Python, so it's blazingly fast, and it allows you to do a lot of actually analysis like this. So now having this thing, we actually can go and scatter and plot the plots. So here we have a scatter plot of hits in this vertex detector, and it's interactive, and each plane colored by its own color. So actually the list is over here. And it was really easy to plot, because I just say that I want to X and Y be X and Y, and I want this volume name to be a color. So if we go to the next plot, we plot actually the same hits, but in 3D scatter plot. And just to change something, we used energy deposit here as a color of each hit right? So since everybody of us actually get used to histograms, here's the way, for example, how to plot a histogram out of the same x and y, hits. And finally, there's something else. There's actually hits in planes of gem detector layers. And that's one more 3D plot. And actually, all the system allows really easy to kind of filter and stuff. If we go back over here and you see this thing that we are just asking, for example, this data frame, give us all hits which with a certain name of the detector, and it just gives us the name. Okay, now let's go forward with actually kind of our reconstruction frame. So we spent a lot of time with reconstruction framework was running this Jana stuff on January 9th, and there going to be a full reconstruction tutorial we will cover fully in detail. But the idea behind this is that our Jana reconstruction framework knows how to open and how actually to deal with file produced by G4e, right? So you can easily just run this PyJana. Jana, it's one more library that's actually wraps the Jana and makes it easy to configure. And let's run it. So it will actually run. You may see, it may say that there are some errors. That's actually not errors. It's just we are just running in the container. And Jana is highly parallel framework, and it's trying to get the CPU info, which is not available in the Docker, right? But finally, it's processed these events. So what actually happens? So Jana consists of these plugins. I will not go into details really because it's not the Jana tutorial. But one of the plugins actually allows to read G4e files. And another file is this OpenCharm analysis by Yulia. So we would like to run this analysis. Finally, there is a plugin called Jana itself. It just gives the commands to Jana, and we say that we would like to produce hello process root. And let's see, it should be over here. So when we open it, there is an OpenCharm directory which calls for analysis. There are some plots, and for example, we can draw this histogram. Certainly, we processed not too many events, right? And it's not too many, but anyway, that was the way how we can proceed with our simulation framework. We will have a tutorial about this later. Okay, let's proceed to 2.4, Jupyter CC. So I hope that up until now, you've got everything working flawlessly. But what will happen if something stuck? If, for example, you run the jump for too many or something hangs or whatever, what's actually happens? So this is a little bit. I have to tell you what is actually this Jupyter, how it works, and how you can tame it if something goes wrong. But for this, I have to tell you about how it actually is structured. So we are now working in browser. So when you can guess, this means that there should be some server. So the server runs in Docker image. And actually, when each notebook has so-called a kernel. So the kernel is a process in which actually those things are running. So right now, on the top, on the right, it says Python 3. It says that right now we are running on Python 3 kernel. So as I said before, in this notebook, there's also a root kernel, root C++ kernel. Just don't follow me, I just quickly show you. So if I say I want to create a new notebook, there will be a possibility to create a new notebook with root C++, for example, right? Just don't follow me, I just quickly show you. So this kernel is a process, and you have a special menu which allows you to actually interrupt the kernel, whatever is happening with that. So restart the kernel, restart what's actually happening beneath it. And on the run menu, there's a good command which tells not only run command, but actually restart kernel and run all cells. So it actually just resets everything. And finally, on the front end, you can always, if you have some glitches, can actually reload the website, and everything which is saved will be saved. So there's actually a start of answering this question about how things are organized and if you should run this way a large large number of events. So basically, this Python library and this Jupyter lab just launch some process on a machine, and then it goes to a question if you would like to run a jump with many events on your machine, right? Or on some machine where this Docker is running. But I will answer this question many times during this presentation, again and again, for different things. Now, let me actually answer one more questions about this. It's common questions about this Jupyter and stuff like this. So let me go quickly back to the presentation. So first of all, okay, I introduced you John today. I introduced you John's running in Jupyter. So what, you have to now work with Jupyter? The answer is no. This stack, which we have and introduced in this Docker image, consists of layers. And on the top layer, we have a Jupyter lab, which is extremely useful when you do a tutorial, for example, or, for example, publishing some results. But if you don't want to use it, you can just go to level deeper and use Python. Right? If you don't like Python at all, you can just go a little deep and just use C++ with your beloved editor and whatever you like, and like this. So actually, to continue with this, you can run this Docker without Jupyter Lab. You can just add bash in the end that you will be ending in the bash console. And actually, the reason behind why we are using this Jupyter right now and why we are pushing it, because it provides a very convenient way to organize software so that it actually represents your workflow, which means that we will have Jupyter installed in Jefferson Lab and BNL on special servers, having access to all these disk systems, right? It allows you to run some configuration and make sure that actually it produces some plots, which is okay. And then we will actually have a button now, okay, I like this configuration, now send it to the OSG or other farms that we will have. And actually right on the Jupyter notebook, you will have results. You will have updates, and finally you can process the results. And if I promised this probably on August during this user group meeting right now, saying that we have started to work on it, now I could say that we are very, very close. So there are actually several solutions used for that. And actually those solutions already kind of an alpha version, so we are running things from Jupyter to server. But we are just probably will have another tutorial or something about it. Okay, but still, if you don't like Docker, this container has another thing. It has a no VNC server. So if you open another tab and open localhost, in your case it's going to be 6080. Actually, if we go to the next example using VNC, you can just copy paste it from here. Right? In my case, as you remember, I changed the port, so in my case it's going to be 6090. So we are going to no VNC. It allows to run VNC clients right in your browser, and it actually has access to the underlying Docker container. So if you put this simple password 123456, you will get inside, and that is why this Docker container called Jana epic-GUE, because it has this environment. So in the sake of tutorials, you see I have the scaling problem. To solve this, I can run over here settings, and then there will be clip to window, and I choose clipping with remote resizing. So you can do this the same way. So it's settings, clip to window, remote resizing. And just in case you wanted to actually kind of give your clipboard to this VNC or something, there is a clipboard window which you can put it there. Okay, so let's actually run something in this VNC environment. So the next is 32, which actually just a Python code, which has everything like in the example above, except one thing. It adds this function called .vis. And as you can guess from the name, it actually says that you want to run the Junt and this thing in the event display mode. So let's actually do the following. We pick the application over here. We click the terminal emulator, right? So we are now locating in this tutorials example. So, oops, let me go back. And we go to CD to 0.2, right? And we want to run Python 3. 3 is important here because Python 2 ended its life, its support in last year, right? So it works as Python 3. And then 32, I just pick slash this event display VNC. I hit run, and it actually runs Junt now in your console. And it starts standard Junt Qt visualization. It actually takes some time because we are now running in software rendering mode on the Docker on Windows, which actually uses VirtualBox on this, and VirtualBox uses terminal. Okay, so we rendered it. The camera is a bit far, but we have this one. We have this image and this 3D picture of our J-like detector with BNL beamline. And if we go back, for example, to this file and put here J-like, I want to save it, so Control S, and I want to close this one and run it once again. So this is already a J-like beamline. So it's pretty easy to actually switch. All right. Let's go back a little bit. So if you are running this Docker, especially remotely, and you can nowadays can run Docker from whatever they want, right? You can access it through browser, and actually it has some tools for coding. So once again, if you don't want to use Jupyter, you can use. So there's for example, this VS Code or its free version Codule, which is full-fledged IDE, which if you open the G4e, it will just grab all the projects just out of the box with CMake, and you can just instantly actually configure and run anything. But I don't want to go into this VS Codium tutorial, so let me go back a little bit to the presentation. So still now we are working for this browser, which is pretty good for tutorial and maybe good if you are doing something remotely. But there's actually at least five ways how you interact with this Docker image. So it's a Jupyter Lab, it's no VNC. You can actually run any VNC player, whatever you like. You can actually connect it with X11 and have all those windows rendered by your machine, but it requires additional configuration, which actually, and that's why we're not using it for tutorial. There's certainly remote debugging, and there's also an option just to install everything on your machine, open with your beloved editors, and just run. It's really simple. We'll come to this a little bit later. Okay, now let's go back and forward with the tutorial. Just a little bit, because we are coming to the second part. Let me actually switch this picture over here. So we are going to the second part about how we import detector, render detector, and show list. And before this, I wanted to actually show where is the software by itself. So we will cover what is this Junt, how it's created, but where it is. So you can actually, in Jupyter, you can run any command with exclamation sign, and it will be run actually the console command. For example, ls, it's just the console. And one of the packages they're called EGPM, which calls, which is kind of a package manager which we use for building the applications. If you run it, it actually just without any parameters, it just say where is the software installed in the Docker image. So if you will be hacking the Docker image, it's there. Also, for example, the next comment will just show all the directories and all knowledge about the G4e, where it is installed. And if you would like to install this software on your machine, it's really easy. You just go to the CGPM website that have a common instruction, but basically you just install EGPM with pip, Python pip, you just pip install EGPM, and then you set which directory you would like to install everything, and you say, I want to install G4e on my machine. We tested it on Linux, on Ubuntu, on Red Hat, and on Mac. It works now.
You mean instead of using the Docker?
Yes. I mean, you can start with Docker. You can start with this. The idea is that you can start with Docker. You can familiarize yourself with everything, but then you can just open it up and whatever tools you like and run. So now there is a very important step for the rest of this tutorial. So we wanted to run this command and to create a link over here to the installation of this G4e. So this ln -s, I already told you where you get this thing, and just run it. So the rest of the tutorial will assume I just run it. And yeah, here we have a directory with G4e. We will explore the code and see what's inside. But before we start doing it, just once again, run this thing. The rest of the tutorial will be actually depends on this. But I will repeat this several times. Let me actually now go back a little bit to presentation and show you what is this G4e, how it works, and what is inside. So first of all, this G4e, it's pure Junt. Everything is done in a pure Junt way. And actually, the idea behind it that if you are a Junt developer, and we hope that it will be convenient for Yellow Pages Detector developers if they are Junt experts, to actually navigate and browse the code. So we try to kind of have a small code base, except for detectors, right? So everything is done so that if you're familiar with Junt 4, you should be able just to figure out what is where. So the usual question, where is your detector construction? We'll have answer, here is our detector construction, and other stuff, right? And it's because we're just providing it as a source code, and the source code is close to Junt, you just can do whatever you want with a Junt and Junt code and Junt example. So it's absolutely pure street fight or bar crawl, right? But we actually have some recommendations how the code is organized so that it serves its goal. And the goal is the same. So right now this G4e has different beamlines, and who know what's going to be the updates and what's going to be in the future. Then it also called a master detector. So right now, you know, at least 4 of them, 3 is active, is J-like and Phoenix. So right now we have implementation of J-like, and we have 2 beamlines over here, but actually it's kind of everything organized to have other master detectors. And finally, we have a number of detectors, sub-detectors, and each of them can be actually configured so that it's used, for example, for J-like or for Beast and J-like. Looks pretty much alike. So, from the perspective of detector developer, you're actually sitting in this green line or in this green box, right? I'm developing this green box. And what you need is basically a configuration where it actually comes to you. So, okay, what is the beamline? What is the J-like? So you can actually make some switches. So we will go through how it's organized in this way. So, so if you're a detector developer, there are 4 ways right now how you can actually put your detector to this G4e. One is you just create and hack a detector right into the C++. We'll go run the example. The second one is if your detector lives in separate repository and compiles to library, you can just hook this library and add it to the code. We'll use this Lumi monitor for this. So if your detector is implemented with geometry, it's possible actually to import it we're using the VGM. So the example is upcoming. And finally, as you know, the Junt now has this Python library, and we don't see obstacles actually having this detector. I, by the way, haven't seen anybody really using Python for defining detectors, but it's possible. I saw basically notebooks, and why not, if it's possible.
It's part of Giant 4?
Yes, part of Giant 4, and even
know that.
yeah, it's coming there for actually already a long time, but it required additional compilation. Now with Giant 2.10.6, or maybe the next version, they're starting to include the compilation in the main compilation, so it will be compiled every time with Giant 4. But yeah, it's official Giant 4. And actually, before we're going forward to start hacking the detector and something, I wanted to show you our detector naming convention. It's not that naming convention that is going to be, that actually Marcos mentioned today in the morning, but maybe it's pretty close to it. And the idea is that everywhere we have detector names like this, for example, CB VTX, where C means central detector, and it has actually three parts: electron end cap, barrel, and ion end cap. Then we have a far forward ion, and then we have far forward ion, and we have far forward electron area over here. So when we go to the C++ code, your actually coding taste may say that, hey, you are using everywhere such coding conventions like this. It's not like you usually do in C++. But the idea behind it that with all this stack and with all this G4e, we have the same name. And so this name is kind of unique. So you have these names in C++ code, but then you see them in the geometry, you may see them in reconstruction, and when they are kind of all around, it makes them more convenient to work with them like that. So since we'll be using these names, I wanted you to know how to do this. Okay, now we are ready. There's one more examples of this naming. And yes, finally, what I wanted to say that in our implementation, all detectors are kind of, we have a hierarchical representation, like we have master volumes, then we have a subdetector volumes, and in the IX volumes are subdetectors. Okay, let's actually go back to coding and running the tutorial. Let's go to this 42 called Explorer G4e. Okay, so now we have this G4e folder with the G4e code, and I just want to quickly say that in the source directory, there are the two interesting directories. One is mine detectors. So right now there is a JLike, and if you wanted to actually have a detector construction, here is our detector construction. Just like this. So for Giant experts, it should be actually pretty convenient. And the other important directory is subdetectors. So here the list of subdetectors. Some of them are just stubs, some of them just volumes, some of them has more details. We will not go into details right now. So for the next tutorial, we are going to create some subdetector, maybe with some basic volume in it. And it means that we should create some right directory, put some right stub file, and actually we can introduce. So if you please go to 501. There's one more Python library called Giant4 EIC Manager. It actually allows you a little bit easier to do such things like adding detector or rebuilding the Giant. Yeah, and by the way, if you go back to the 4.2, there's a quick step with the same Giant4 EIC Manager to rebuild it. Right now we didn't have any changes, so let's quickly say that it's already done. So once again, there's no miracles. It runs CMake underneath. Okay, so let's go back to 501 and run this first. We run the import Giant AI Manager, and then we run this add subdetector, and we call it FFT Lumi for luminosity monitor. I know, Yaroslav, that you everywhere named it Elmond. But in our case, we kind of called it Lumi, and I already used this for this tutorial. So let's run it. and actually tells where it created a file. But you have this link over here. If you just click on it, the Jupyter Lab is smart enough just to go to this file. So this file, we call it Detector design file. It's just a stub file. Right now it's pretty much empty. And it consists of two objects, one of them called FFE_Lumi_config. Now your feeling of kind of great naming conventions in C++ should be screaming, but take it as a fact. It's in the end it's convenient. So and then it actually creates some class Lumi design, which has a construct method which accepts this config, and it actually has construct detectors method. It has pretty obvious logical physics, everything in it. And it has some strange commented out constructor with thing called Initialization Context. We'll come to this by the end of the presentation. Now we will try to make everything as simple as possible to get to the first results, right? So by itself, this file actually does nothing. And let me close some previous windows so I could at least see this thing. So let's actually fill it with something, right? So first, if we created a new detector, we have to add it to detector construction. So in our case, it's just no miracles. You just go to the detector construction.h. And by the way, yes, that's a very important announcement. So now we have started to change the code, right? And I await that if you will follow me, you can come up with something is not working, something you didn't copy pasted, whatever. There will be two shortcuts in this presentation, in this whole tutorial, where you can actually get everything working. So, so please try to follow. If something is not working, there will be a place where everything will be synchronized and you should have everything working. So, okay, going to detector construction, and we just want to include this header for the new created detector. Just go over here and we find some place called far forward electron with already something in it, and we add Lumi down there. And as you can guess, we should add a class member, right? To it. So we just wanted to go a little bit down into detector construction. A little bit, up to down. And actually, yeah, already we have a placeholder for the Lumi. And I hit Ctrl S to save the file. We are done with it. So basically, as it was said, we find that it's okay that the code might be changed. So because we
Dimitri,
yes.
The template generator generates an identical include protection. So if you include two of those files, you basically bomb out. See if you got this G4e template HA.
Okay, that's actually no, that's actually a good bug report. Thank you very much. Yes, actually, it should instead of template, yeah, instead of something actually, instead of template, it should be FFE Lumi. So, yeah, but for now it's okay.
Yeah, sure.
Yeah, but thanks for the bug report. Right? So let me go back. Okay, so we're done with H file. I can actually close it. And right in the end of this J-like detector construction, we want to actually add this Lumi monitor. So as you can see, there's from one point of thing, there's nothing like miracle. That is actually kind of a decision that we don't want to automatically generate or change the files that existing, because it should be up to you. So we help a little bit to create the right directory, right stuff, but there's nothing in putting the stuff in this detector construction, right? And then, yeah, let's try to rebuild it. It should be working. Yeah, I figured out it takes much longer time on the virtual machine on the Docker on Windows that it's regularly done in Windows. By the way, it's just Lux, so it's already proceeded a long time ago, but for some reason it just Lux. Yeah. So while it's compiling, why not just going a little bit further? Yeah, we actually don't have to build at this moment. So the interesting moment is going to be over here. We'll try to add some stat volumes to our this FFE Lumi file. So we first add the 3 very simple lines to the construct method, which creates just physics logic stuff. And that's going to be our kind of outer volume for this Lumi detector. And then we want to, the second one, we want to uncomment probably this visualization attribute, right? So because we want to this volume be displayed. And finally, we just copy paste these parameters to this config. It has some example parameter. Yeah, but let's just move it. So let me actually explain what is happening with this config, why we have this config, why we have this design, and what is actually happening behind it. What's the logic of organization of this stuff? So, on the left side we have our mine detector construction, and we actually try to configure everything in it. On the right side we have a sub-detector implementation. And this line in the middle say that actually they don't have to know about each other. So, for example, there's going to be the full library of Yaroslav, right? So, and we're using these 2 simple classes, detector config, and which actually pushes the config from the master detector to sub-detector. So, sub-detector can create itself by providing actually master volumes. So, that is something that works like this. Okay, let's go back to the presentation, and we will actually cover this in more details later. So this thing is done compiling. We add everything, and yeah, probably we want to, since we changed the FFE limit, so we probably want to run the compilation one more time. Once again, it's ridiculous for me why it's so slow in the virtual machine. It doesn't affect things. Running on the same laptop like this, and when you have changed just one file, the compilation takes 20 seconds. I just measured it before because we're trying to keep kind of compilation time slow. But somehow on the Docker on the virtual machine, on the virtual box, whatever, takes longer, probably because of the I/O or maybe something else. Yeah, that's done. So let's test what we created. So I will just run the same configuration as I saw before. I will put beam on 1, just one event, because what I want is just to create a geometry, basically. Maybe run one event. Went through. It created the test FFE Lumi file over here. And we can actually click to the geometry. And see that we created this large ugly volume, and we will develop them in future. So basically, if you are creating your detector, writing the G4e or putting it, you can use this detector design as a gate cloud detectors, right? But now let's go back to the next and maybe the most complex and important part is how we import the Lumi library, which means the standalone Jant4 implementation of a detector right from the repository. And now I wanted to say about the shortcut. So if you are trying to follow this instruction and something is not working and you are it's hard to fix too, there's a file called 70 shortcut, which actually has all the commands, which if you run from the fresh Docker container, if you close this, don't do this, but just in case something is not working, right? So if you close the Docker, open it once again, and just run all the cells in this final shortcut, you will get to the final result that you will have in the end of this tutorial, by the end of this tutorial, right? And it's also good if you will be running this Docker in the evening, and okay, this Dmitry showed how to do this, but how I can repeat it myself. Here is actually all the step, you can run it. And this shortcut was one of the updates I wanted to do in the end. So there is a final FFE Lumi. That is the final version of Lumi we will get to the end. But you see it will not change actually much. But let's close it for now and follow with luminosity monitor. Okay, I go to 60, explore Lumi monitor. And first thing, I just download it from the GitHub. Why not? Let's be fair and just download it and start from scratch. So you see, and before, don't click the next. Actually, I wanted to a little bit. Oh, you may click. Don't follow me. I wanted just to show a little bit the code inside this Lumi monitor, right? We call it. If we open it, so you see the internals of this repository. First, we see that it's created with made with CMake, and if we open the CMake, you will see two things. It creates a library with the detector called det. It's not really kind of self-explanatory name, but okay, let's remember this, det, the library named det. And also there's a run cxx, which is pretty standard, pretty nice written like an examples initialization file for G4. Now let's go to the source. First we have, First we have action initialization. And that is, we see the action is used actually this TX threader. I know that is a event generator action. And now there's two user action, event action and run action, which is used for this detector, right? And finally, we'll go to the major stuff. Where is your detector construction? Here is the detector construction. And you see it's it's not very long, but what we see from the library here is that first, it still have some custom stuff, like it creates detectors, it actually creates root file, it iterates through this detector, so it has some logic, right? So we don't want to copy past anything, we want to kind of just import, trying to use whatever logic is used by detector, right? So the other thing we see, which is actually will need our a little bit change, that probably was one of the changes you did with the same thing, that it creates its own vault in the detector construct, right? Because while we importing, let me go back to actually, okay, I closed everything. Well, let me go back to this. To this file. So here is actually plan how we should import this detector, right? So we have to connect its CMake file, its CMake with our CMake. Then we want to build its geometry. So, and in this case, we just want to call its detector construction. We don't want to care about what's behind. Then we need to link user actions. And then we want to provide some kind of additional configuration and what is the root file and whatever to this thing. Yeah, final thing about this monitor is that it has some kind of root run mac. And if you see this run mac, it has custom macro commands that we don't want to forget to use in the end. All right? So we're just importing detector with all its logic, with everything just inside our G4e. So let's do the next comments. First, we just move this luminosity monitor to its this folder to its right place. So it's in SRC subdetectors and its folder. that is the same folder where this ff Lumi design file lives. And then for the sake of craziness of JIT, I will remove this JIT folder. But in reality, you can install your detector with subproject, or you can just use compiling library. In this case, because we're changing Lumi a little bit, we will compile it with G4e together. We'll change it now and a little bit. So first, add it to CMake. So each hour, just open the CMake file. Each hour directory has CMake files, and the subdetector lib has CMake file too. You can just click on it to open the file. Actually, it's empty because our detectors, most of them are header only. We like header only, right? So, but please add these two lines to the CMake file, which actually would add subdirectory this FFE Lumi Elmon. So it's actually add this project to our CMake. And don't be fooled by the comment. Please replace the comment because it's target link libraries G4e det. Do you remember that this library, luminosity monitor detector library called det? So it's that. Where is that? That is that big. Okay. So we linked it. We can actually we link it. I saved the CMake file. I can actually run CMake configure out of it. It actually configured. And once again, the command is nothing fancy. I just run CMake and that's it. So right now, if I run the build, it will take some time, as you know, on this virtual machine. But I mean, like 1 minute. But we don't want to waste 1 minute. But I would say that nothing will happen because, okay, we put the library, we put this on, but we didn't really put the sub. Okay, I pressed this button. Okay.
Dimitri, just from my knowledge, the build is done in a different directory as you normally do with CMake, and the installation is done.
It really depends. It really depends on how you configure CMake.
Yes, that's the reason why I'm asking.
Yeah, so there is a in place CMake builds, right? Mm-hmm. So there is also a not CMake. If we go back, just
you use it in place or you use it.
I will just show, right? If we go to this 41 import to software and run this EGPM PVD G4e, it just tells you where is this build directory located. Mm-hmm. So here it is.
So you have a build directory.
Yes, we have a build directory, and in this case,
an external directory, which is.
Yes. So in this, for different packages, we do use different strategies. So for root, it's certainly kind of a bin directory, whatever. But to make it easy to hack with G4e and just run it and whatever, we're using kind of half in place build. So which means that there is no separated bin directory, like what we are using this CMake inside the same directory. I hope it's answering your question. So, okay, the build is done. And if you actually look at the log, it first takes and builds this luminosity monitor. Okay, now let's make these changes to, let's actually make some changes to luminosity monitor because what is preventing, that is this file. Just don't run the comments, let me actually explain. If you open this detector construction of luminosity monitor, you will see the construct method, right? And you will see that that it creates its own volt volume, right? But we have our volt volume, and we would like this actually luminosity monitor to create to be created in our volume, so to be created in volume we provided. So I hacked it a little bit with there are actually two files of this hack detector construction. Please don't follow me. I will just show approximately what has been done. So we create second construct method. So the first construct method, which actually constructs all detectors, it just accepts its top volumes like this. I'm just showing it for the simplicity. Sometimes call this right, and then we just copy paste everything and actually create the second construct method without parameters. Okay. I should copy it first. And then, so in the end, it actually don't follow me. We will just copy the right files to the right place. I just wanted to show what we are basically doing, and I wanted to show, demonstrate the next thing, that by changing this directory, it doesn't lose its ability to be a standalone giant repository. So right now, if Lumi Monitor is compiled with Yaroslav without G4e, it will just use as usual its construct method, right? But we, in our directory, can use this construct method, which just gets the top volume. Now, if we go back, there's this two CP comments, which actually just copies this changed files to the right places. And then finally, we want to add this luminosity monitor to our detector, to our detector design file. So unfortunately, I close it. But first, I didn't add a link here. There's probably something to improve, right? So I have to go manually to SRC, subdetectors, Lumi Monitor, and I wanted to open this design file. And I want to add somewhere in the private section the detector construction. So once again, in Luminosity Monitor, it doesn't have any kind of prefix, it doesn't have any namespace, it's just called detector construction. So we want to add detector construct in this construct detector methods. And there's actually a question why there's two methods, one construct and not here actually. Here, sorry. Why there's two methods, construct in this designer and construct detectors. So as we said, we're using hierarchical design, and sometimes we just don't want to have all the details of the detector. We just want the outer volume. Sometimes it's enough for us. So the construct method is kind of outer method, just to construct outer volume, and construct detectors is actually a method where all the subvolumes are constructed. So so now we want to call this detector construction construct of the Lumi Monitor over here. In this construct detectors, right, like this. And actually, that I forget to mention, if we look closely to the sizes of the detectors that are created on Lumi monitors, we want to change our config too. We want to make this larger. And actually, at this point, I believe it's pretty hard to follow me. So you have this shortcut actually. So you can just take the final Lumi monitor located in the detector tutorial, just copy everything and paste to our detector tutorial. But basically, we didn't do, once again, anything magical here. We just added this detector construction from Lumi monitor. We just constructed, we just constructed the outer volume, and during detector construct detector, we just calling construct of the Lumi monitor. All right. So finally, we call this function detector construct detectors, and we want to add this method also to JLike detector construction. So in the end, where our luminosity monitor, we just add this. So it should be a little bit different. I will talk a little bit about it in the end, but for now we just want to get results as soon as possible. And what else? Is there anything else? No, that shouldn't be, right? So we can try building it. And we should see this luminosity monitor geometry in our geometry. So actually, if you've been lost at this point, there's a 67 called final check. And it just copies right files to the right places. So it just takes the final this Lumi monitor and copies this to the right place, as well as final our J-like detector construction. So if you are still following, and if you want to see the results, there are. So this is done. Here we have a build. Yeah, okay, it builds. So everything builds. Let's check that the geometry of luminosity monitor is there. And do you remember that we have to add some additional macros? So here how we add it. There's a one more common function called command. So let me actually play this. It runs jump. It processes one event. It calls test full. Let's actually go and see that something is there. We can do this with this browser. Yeah, here it is. But it's actually black and it's not really representative. So for the sake of the kind of full showing that it's the same as in Yaroslav tutorial, let's switch to the VNC and run this file, which is actually just a Python file with the same configuration. So I wanted to run Python 3 with 65 underscore stuff like this. It takes a little time to. Okay, here is the result that we wanted to achieve. Actually, let me switch to move. So here is this luminosity monitor with home calls. It's a bit out of the size of the detector, but for the sake of this tutorial, we will not go into details because it's just already a relocation, reposition the stuff. Let me actually a little bit zoom in for this concal stuff, right? Because I see that Yaroslav is now looking interested and smiling. Yep. So right now we will end up this interactive tutorial on this because now it's kind of an expert work how you can move the detector to right place, and it's pretty simple. And we will go to the next actually stuff, which is okay. We demonstrated how we can actually import this detector as geometry in our stuff. And what actually happened that we just created a single file with detector config and detector design, and this file is used to actually communicate between master detector and detectors. Also, if once again I wanted to actually emphasize this, if you will be trying to do the same by own, there's this 70 shortcut. There's the last notebook in this tutorial, which if you are running fresh with fresh Docker, actually allows you to go through all these steps and just get the final results. And you can go through the tutorials, or you can go through the shortcut. It will yield you the same stuff. Okay, let's go back to the finishing slides. So how actually now, as you remember, there was the stepping actions, not stepping, but okay, if it were stepping actions, it would be. Right, there was event action, there would be run actions. I'm actually not showing how to link them because they have a problem there. They called, should I show you? Yeah, okay. So the problem is like this. So if we open source subdetectors Lumi. Here it is, and here's the library Elmo. We open source detector, and we want, for example, event action. Where is the event action? Oh, here. So in event action, what first happens? It's called run manager, get run manager, get user detector construction. And then from this detector construction, you run begin event. But right now, and that is actually kind of these pretty much very well-known issues. You should never use global objects. You better avoid singletons, and even service locators are bad. So in this case, it's going to be J-like detector construction, which will certainly not have begin event stuff and like this. So just don't use singletons. There are a lot of stuff like injection, dependency injection, whatever, which is used. It's really easy to actually to fix, right? I could change these files and put them there too. There's no problem in it, but it's just already too much for this tutorial, right? So I'm just saying that, okay, let's imagine you have this event. I actually did it in the first place, then I figured out that this tutorial is kind of starting to run longer and longer, and I already see that everybody is tired, so let's finish this up. Okay, how you link event actions? So normally you have action initialization, right? Where and action initialization actually is using when you are running Jant in multi-threaded mode. In multi-threaded mode, each of your sub-workers, thread workers, actually should have its own event action and some other stuff, right? So, but if we have many, there's this, for example, multi-stepping action class for in Jant, which allows you to add several instances of stepping actions, right? So, for example, each subdetector may have any number of stepping actions. But the problem with multi-threading that we have to kind of each time create a new stepping action for each thread. So for this, we have this multi-initialization. Okay, I see that people are already tired. Okay, I just say that you link this stepping action or staking action or run action or whatever with just one line like this. You just provide a lambda function which actually creates your stepping action. That's it. The other question would be, okay, it creates a root root file. It creates and if you remember, all output file names has the same base, like everything old at the beginning of files are the same, right? How you can get this name from Detector. And here we came to this commented out constructor where so-called initialization context is used. So actually for each detector, we provide this initialization context, which is interface to all the configuration which we needed. So if we look back on how actually this thing is organized and how this works, it looks like this. So we have a number of subdetectors, and each subdetector has a number of kind of its own configs. And for those in those configs are those fields that are relevant to actually build and configure the detector. Then we use our master detector construction, which actually just goes to subdetectors. It takes its configuration files, it configures it the right way. For example, if you switch off the part of the, if you switch, for example, beamline, or you switch off parts of the detector is possible, but then everything else will be shipped. So all the shifts are taken into the logic of my detector, and they are actually submitted to subdetector. Subdetector builds and going back. And finally, to have a full picture with the initialization context, it's working like this. So each subdetector have its subconfig, which it works. So it's just a single file. It's actually pretty pretty simple. Okay, now let's me finalize it with some kind of usual question and answers. I hope that we finished with actually inputting the detector. So usual first question is how do I save the data, right? So we showed how to run the stuff. So how should I save the data? So first we run this Docker image with rm flag, which actually removes all changes, so kind of reverse all changes that you done for Docker. When you're running yourself, you probably don't want to run with this rm flag. And then this Docker will run like a small virtual machine. Okay, so then the next question, how you can process your file, for example, your Monte Carlo file or whatever, get access to your system with this Docker image. And it's done with one more flag, which actually binds your folder with some folder on the Docker. And we propose this Docker with this folder because you will see it under the Jupyter environment. There's also a little problem with Windows on sharing, but it's easy actually to Google.
Dmitry?
Yes?
Oh, sorry to interrupt. So what exactly this RM flag does?
What
exactly? So what it saves and where?
No, it's not saves. It's actually, so usually when you exit the Docker container, Docker continue to live with your changes, you can actually reattach the Docker and have all the changes in the Docker. RM actually reverts us back. So like you are just downloaded the Docker.
So this is something different from mounting with -v the local.
RM actually doesn't relate to mounting.
Why not?
Because
that's too different.
I found this more convenient in some sense.
What do you mean? I mean, this is two options. So this is RM refers to internal Docker file system.
Yes.
Right? And this actually refers to your file system.
Oh, you do have -. Okay, sorry.
Yeah. Right? Then actually, if you will try running debugging those things in your Docker, you probably will find that debugger is not working. So you would like to add more flags that allows Docker to run debugging, so some opening some kernel stuff like this. And also, if you would like to actually connect with your VNC to open the port. So then, how to install things on my machine? I actually already showed it in the examples, but I wanted to say that right now we are concentrated on the containers, and there is this EGPM which allows you just to run EGPM, install G4e, and build it on your machine if it's Linux or Mac OS. And it's a little bit on your own risk, but more or less we tested it's working right now. Definitely for the first two tutorials with fast simulation and full simulation, actually we didn't show everything maybe needed. So they are going to be, we are going to repeat the same tutorial on February 6th in Jefferson Lab, but it will be available on BlueJeans. And if you would like to send some students for it. And there are probably a lot of topics that are now not covered. We're talking about making the reconstruction tutorials next. And please stay tuned. We will provide you with this information. So the very important message is that we really need your input. If you are trying to do something is not working, please contact us. Or if you have ideas, please contact us. Because having this simple EIC stuff, this G4e stuff, is actually our desire to grow the software with the user input. So to actually have it initially designed for it and actually to grow it whatever you want. So if you will come to us and say this, I need this feature, you will be more than seriously accepted. So if you have any questions, so there's actually a link where the G4e is located and where you can grab the eGPM. And we also have support team working, so we can answer any question on a number of channels. So thank you very much. And we're actually coming to questions, your questions, and maybe showing some stuff. So thank you.
Thank you, Dmitry. Very nice, and thank you for all the hard work. Very much. And January 9th one.
So this is Tom Hemick. I just have a simple question because I think the before and after lunch presentations had a very different philosophy. If I understand what happens in before lunch presentation, in this case, your code is all compiled in advance, and at runtime, you load shared object libraries and you write macros to which detectors you do and do not want. And what you've shown us is a very extensive and extremely impressive Jupyter notebook where I believe that what you're doing is you're changing the code to reconfigure the detector rather than changing the macro. Am I capturing those distinctions correctly?
No, not really. Actually, so first, yes, our philosophy that since that for a simple task or simpler task, you might need a simpler tool, and that you can just benefit if you implement everything in the pure Jant and as simple as possible. So that was a key principle. But that is not kind of clear what you're saying. That
I guess.
So, no. Let me finish, please. So we use standard Jant methods, and for those, it's macroses, Jant macroses and Jant parameters. And to create, if you would like to change some parameters outside, the simplest way how you do this is with just one line. Just let me show you. Right?
Okay.
Just let me show you. And by the way, okay, if we are in Lumi monitor, actually Yaroslav making the same. So it's just one line of code. If you would like your property or something to be controlled without recompilation, it's just one line of code to add. Okay, let this configuration parameter to be controlled from the macros, right? And then, as we showed in the tutorials many times, you just configure the macro whatever you want, and you can run it without rebuilding. But yeah, on the terms when you are developing your detector, it's probably okay to rebuild stuff if the build is fast. Do I answer your question?
I guess so. I just think that what I was seeing was whether or not you have a luminosity detector is being changed prior to compiling. And maybe you're telling me that I'm misinterpreting your presentation, and that could be my fault.
When you put a new detector, you have to compile it.
Yeah. That's
no, you don't. Not in Fun for All. The detectors are compiled in advance, and the list of detectors that are your configuration are registered to a system that holds a vector of pointers to base classes. So at runtime, you decide.
Yeah, it's a little bit tricky philosophical question. I'm sorry that because
I was just trying to understand the difference in the two philosophies.
Okay, let me actually explain this philosophy to you, right? So in both frameworks, actually, right, you have some code. So, for example, in both codes, you have some code which is compiled, and you have some code which is run as interpreter, be it C++ interpreter or Python interpreter, and you have some configuration which can be saved in configuration. So we use configuration macros, for example, Jant4 configuration macros, right? So it's kind of all the same. So it's a kind of a little bit, it's a little bit different philosophy, but really it's not that different. One cannot say that, okay, we are not recompiling. Because you are running anyway, you are running, okay, you are not recompiling, but you are iterating run this.
This morning I remember a configure, a make, and that was compiling.
Yeah, exactly.
I don't think that if you install a new detector, or you have already the classes there, but if you
but whenever you take a detector out of there, put another one in, you have to recompile. It's not done on the
No, not really. Actually, I can give a word to Yulia. So, for example, right now you can, without recompilation, just with macros, for example, switch off the internal.
No, but sorry.
You create one flag and say, like, if this flag is on, then you have the detector flag is off.
This is true. When you have done the detector, you have a flag, you can put it on and out, in and out without recompiling in your code. That is what I remember. But to develop the detector, you need to compile.
Yeah. To finalize this question, we are just using standard Jant4 tools. We are just sticking to Jant4. How Jant4 solve this problem? Okay. Any other questions?
I have a question concerning when you want to run more events in parallel and put things in parallel.
Yes.
How you recollect this different? I don't know if you will use singularities at that point.
Yeah, absolutely. Yes, absolutely. Yes. Okay. So, okay, I understand this question. That's a very good question. So there are actually 3 questions in it. So I'll try to answer all of them. The first question, actually, how you parallelize things. So we are trying to stick with standard joint multi-parallelization mechanism, right? And we have a parameter called number of threads, which will just use the joint parallelization for it. Right now, it's not working. One of the parts is that we have to, in very small time, like 3 weeks, import the BNL beamline in this stuff. It's pretty fresh. So for this, we didn't test it with multi-threading, but actually we're doing this. So that was the second, how we actually collect them together. So for this, Joint has first its own tools, which called scorers, and actually everything is done in Joint 4. It's just standard Joint 4 tools, nothing special there. Any Joint, for example, like advanced example, whatever do this. The other stuff is root file, because we understand that actually everything, all detectors would like to, because Joint analysis libraries probably are weak. So everybody just do root or do some output and stuff. And there is no actually right now some special stuff on it, other than root mechanism for doing it.
So you chain the
Yes. That's it.
You actually addressed this question, which I also like to ask about compiling versus scripting by using shared libraries and loading them on demand and trying to figure out the contents by detector name or something like that?
Absolutely. You see, we actually wanted to, so like Jana is modular framework which allows you to do this dynamically. We want to get to the point, especially talking about the Greenfield simulation. But probably, Sasha, we can discuss this question in the 20 minutes, right, in this simulation discussion.
Is
Yes.
it available from JLab Q machine?
Yes, and we are finalizing both with BNL. We're actually working together, and Jefferson Lab to have this on Jupyter servers. So like in JLab is jupyter.jlab.org, and you will have just running this machine, and you will have access to all the files, JLab file system underneath. I just know a little bit better because I worked this, but I know that we are both working with BNL and JLab, the same thing, right? So, for example, if you have your Monte Carlo files or whatever running there, and moreover, that's what we are finishing. You can run in parallel on Slurm or whatever on Farm. So, yes, the question is yes. We're pretty much almost
just
there.
like the other one for all, it is already compiled on RCF machine. So if someone has a JLab account, can I access the resource?
You mean this G4e and stuff?
No,
Or
this one.
yeah.
Without Docker.
I mean, in JLab, yes. And if you want CVMFS, sure, we will produce it, but we just created CVMFS organization. Probably Marcus can answer better than I. About, do I understand correctly that it's about CVMFS?
Well, I think the question is, how is our software distributed? You can get it via Docker, you can get it via Singularity. The software is available, parts of it, at the Brookhaven systems and at the Jefferson Lab systems. And as Dimitri said, we are working to have it on Jupyter Hub, both at Brookhaven and Jefferson Lab. And with Singularity containers in both cases, you will also be able to run it on the OSG. For the tutorials, and also I think for a start, we are just under the assumption that Docker is the easiest way to get started with the software. Does this answer your question?
Yeah, but if someone wants to avoid Docker, so just like the other one for all, yes, you can access that using Docker, or if you have RCF account, you can also access that using NX machine. Suppose someone has a PNC session set up on JLab machine, and I have like NX session, I have a separate session over there. Can I have access the full resource without Docker? That was my question.
Just a short answer, yes, and we actually have JLab installation on QM machine. So, but we will actually have it on CVMFS. We just created the CVMFS.
The short answer is yes, and I gave a more detailed answer about all the different flavors which are.
In that case, I just interested to know the path. Location.
What do you mean? I don't understand.
So if it is already installed on JLab machine, and I can access that, so just like the other one for all, what is the location on JLab machine?
So in JLab, it's located probably on the EIC. Let me remember. There's a work group. Right?
EIC up, I think.
Yes.
We send you the link.
You
Yes.
can put that information somewhere.
Yeah.
It's very simple to do.
Dimitri, one more thing.
Yeah.
Imagine that I'm a user. I have installed my detectors there, made my study, but then I like, and also we also like that this detector is not lost. The way to commit to the
Yes, I actually showed, but pretty much didn't put enough accent to it, right? So, and that is excellent question actually, because that's into this intro to the software. So so as you said that it's a G4e repository, and we provide this G4e repository, right? But there's a G4e repository, there's branches like master, and that's what you have to do as a user. First thing is we think that it's actually a best way is to fork it, and then you want to work with your forked version, right? Mm-hmm. So actually with eGPM, it's really easy to reconfigure where you are taking eGPM from, or where you're taking G4e from. And then when you have a forked version, you can compile to us. Actually, there are
actually can submit a merge request.
Yes, absolutely. Like and moreover, if you have, that is very important. If you have any kind of request to help with importing your detector, Yulia, can I actually assign you into? But I know that I can. We with Yulia and actually other people at JLab will be more than happy to help you with that. And once again, as I said before, one of our kind of initiative is have a tool where you can compare things, like really different things, like beamlines and stuff like this. So we are interested to import as much as possible.
Yeah, I think, by the way, I was also saying this morning that this request of support, it would be good if they go to the mailing list or to the tools that we are setting up in the software support, so that also others can see and then see the reactions and answers.
Yes. And that is something funny. Yes. That is something that we with Marcus were approached by Rolf and JLab just to try, just yesterday, or when it was yesterday, the day before yesterday. Yeah, it's actually really actual problem. All right. Okay. Thank you very much once again.
Now, were we going to have a discussion with Elka?
Or she wanted to be here. Should we have a short break until?
So why don't we break until 4? And before we have our